Swayam Prabha. Digital India. Educated India.
So the next thing that I want to talk about is a quantum one-time pad. So first of all, let's recall what is a classical one-time pad. So what's a classical one-time pad? Well, I have some message, right? So, I have some message and some key k, okay, of the same length. Okay, and key is random. Okay, so my ciphertext is just M XOR k. So both are binary. The key is random, randomly chosen. At least I am sure in passing, even if not very rigorously. But this is a very simple idea, right? So it's just that this is my ciphertext, right? And if I know k, then CT XOR k gives me M. Okay. If I don't know k, then this is perfectly random, right? It is information theoretically secure, right? So what is the problem with this? It's beautiful, it's very simple and it's perfectly secure. Why do we not use it? You can only use it once. So it's the information rate is very bad, right? You need the key as long as the message and then you have to throw it away. So this is completely impractical. I mean, basically we have to meet and exchange a key, right, and then go to our houses and do an XOR and transmit it. So we may as well have met and exchanged the message itself. It's not completely useless because we may not know the message at the time that we meet. So it's just like saying that, okay, here's a way for us to communicate secretly in the future. So that is still something useful, but it is not useful enough. And moreover, long time back Shannon showed that this is actually inherent, this long key length is actually inherent if you want perfect secrecy, right. So this is both disappointing and great, because it's disappointing for obvious reasons and it's great because then you can have fun with number theory and so on, right. So yeah, if all this had worked, what would we do? We wouldn't have this course, I wouldn't have this job. Okay. So this is our classical one-time pad, and now what we want to do is a quantum one-time pad. So what does this mean? I want to now encode a quantum state. Okay. So now we are in quantum cryptography, right. So we want to encrypt. Going forward, we want to encrypt quantum states. Let's start by at least doing a one-time pad. Okay. So we have some quantum state, some p, and we want to encode this. And now in the quantum language, what we would like to do is to sort of use some key to change the state to a state that reveals no information, and this is something we talked about in the previous classes. So we want to convert the state to a maximally mixed state somehow, okay, and this will be information theoretically secure if we make it a mixed like a maximally mixed state, right. But in a way that given the key I should be able to recover the original state. This will be our goal, right. So let's build this up slowly. So first I want us to recall these poly gates. So if you recall the poly X gate, do you remember what this gate was implementing? It implements the NOT gate, that is right. Okay. So this implements the NOT gate, and the matrix corresponding to it is 0 1 1 0. Okay. So what it does is that if I apply this gate to 0, then I get 1. This is very easy to see, right. So if I apply this to 0, you can see that I will get 1, right. Let me erase this. Okay, and if I apply it to 1, then I get 0. So I mean that is the meaning of a NOT gate, right. So we get this. Now let us try to think of how to use this. First of all, to just do a classical one time pad. So suppose I just want to use X in order to do a one time pad for just 0 and 1, then how can I do it? The intuition is very simple. If you think of the classical one time pad, okay, just think of a single bit. Okay, so I was trying to hide M, so I was just XORing it with a random bit k, right. So XORing it with a random bit means what? That with probability half the bit gets flipped, isn't it? Whatever is my message bit, with probability half it will get flipped. So an X gate is actually in some way giving us that capability, right. So if I apply the X gate with probability 1/2, then I recover the classical one time pad. Do you see that, right. So if I take qubit 0 or 1 and I apply X to the A, where A is a random bit. So let me say that A is sampled at random from 0 1, okay. Then X to the A is a one time pad. Do you see that, right? So if I take 0, okay, and I apply X to it with probability 1/2, that is being captured by A being a random bit, right. So with probability half it is 0, in which case I do nothing. With probability half it is 1, in which case I apply X. Does everyone see this? It is just a simple idea. Yeah. So I am just saying that X is already giving me a way to sort of get the classical one time pad. But now if I take quantum states, like if I apply X to plus, then what do I get? Can you tell me? I get plus. And if I apply X to minus, minus. Okay. So applying X to these states is not doing anything, right. So it does not seem to help with that. So in order to handle these states, let's use the poly Z matrix or the poly Z gate. So can you remember what the poly Z gate matrix looks like? 1 0 0 minus 1, right. Okay. So now if I apply Z to plus, what do I get? I get minus, and if I apply Z to minus, I get plus. Okay. So it appears that the same idea that I had for the computational basis with X, I can apply that to the Hadamard basis with Z, right. So, I can compute z to the b of whatever state I have, right. So, psi, let us say, right. So, psi is either plus or minus, and b is a random bit. So, do you all agree that this will be okay? Okay. So, again I am achieving the same effect, right. So, with probability half I am flipping it. So, now we have a way to do to handle the two bases, right, and it turns out that actually if I let my key be a comma b random bits, a comma b where a and b are random bits, okay, and I take some arbitrary mixed state p, okay, let p be an arbitrary mixed state. Okay. So, I can think of P as being denoted by the density matrix alpha, beta, gamma, delta. Okay. Then the Q one time pad algorithm for encoding P with some key A B. Any guesses? It is x to the A, z to the B, P, x to the A, z to the B dagger. So, this is my quantum one time pad. So, we have yet to argue both correctness and security, right, but at least the description is clear. So, I have a mixed state, right, I have a secret key just as in the classical case, right, and my secret key here is just classical, so it is just 2 random bits, okay. And what will I do? I will apply x to the A, z to the B, P times the conjugate of x to the A, z to the B. So, let us first let us just get correctness out of the way. If I know the key, how will I decode this state? If I know A and B, so someone should be able to decode it, right, otherwise what point is there. So, if I know A and B, how will I decode it? Exactly, you can just repeat, so you can apply x to the A, z to the B in the appropriate way. So, on the left side you apply the conjugate, on the right side you apply without the conjugate. So, then you will get basically the matrix times its conjugate, right, and these are unitary matrices. So, you will get identity, okay. So, correctness, maybe I'll actually write decode for completeness, or I'll write dec to be consistent with enc, okay. So, dec of the CT, so this I am calling this as CT now, okay. So, dec of CT with AB, right, is just x to the A, z to the B dagger, CT, x to the A, z to the B, okay. So, note that this is unitary, right. So, this will give me back P, okay. So, this part is simple. So, now I want to argue that security holds, right. So, I need to argue that I get a maximally mixed state. So, can anyone argue this for the class? So, how should I argue security? So note, I gave you some notation, use that. So this is alpha, beta, gamma, delta, this is our P, okay, and also here, so alpha plus delta is equal to 1, right, good. So it is a density matrix, so the trace is 1. So now I want to argue that this transformation really hides the state. So let us look at the 4 possibilities. Okay, so 4 combinations, what do they give us? See, it's like the OTP in the classical setting. Even for a single bit you can have a one time pad, right. So now one might say that, oh, but why is this secure, because I can try both possibilities, but you see that, right. Yeah, so if I have a ciphertext which is just a classical one time pad thing, it's just a bit. So your message bit was M and I XORed it with some random bit K, right. Now I, the adversary, I get this bit, right. Yes, I can try both 0 and 1, but what does that give me? So it is the same idea. So let us look at both sort of all 4 combinations of AB. So if it is 0 0, you know, then this just remains P, right, x to the A, z to the B. So this is just just P. So what are the combinations? So you know, you have ZP, Z dagger, okay, you have XP, X dagger, right, and you have XZ, P, XZ dagger. Everyone agrees these are the 4 possibilities, right, okay. The claim is that 1 by 4 times summation AB in 0 1, okay, x to the A, z to the B, P times x to the A, z to the B conjugate. This is we claim that this is maximally mixed. So in particular it is half 1001, this is the claim, okay, and this is maximally mixed, right. Everyone agrees, right, this is maximally mixed. So all the eigenvalues are equal. The space we have on the same slide. So P is just P. Now what is ZP, Z dagger? Can you tell me what is this? So this P is, you know, just alpha, beta, gamma, delta. What is ZP, Z dagger in terms of these alphas, betas? Okay, so I mean it's a simple computation. So this is just, you know, alpha minus beta minus gamma delta, okay, and XP, X dagger turns out to just be, so it will just flip on the diagonal here, okay. So it will be delta gamma beta alpha. Okay, so it just flips the diagonal. And the fourth one is going to be delta beta gamma alpha, but with minus signs in the second and third entry. So that is what Z does. Okay, so if you do both, then you will get both the flip and the minuses. So now can you add them? So adding, what do I get? Yeah, so let's first compute, you know, the top right entry. Okay, so let's first look at this. So beta plus minus beta plus gamma plus minus gamma is what?
0.
Yeah, 0. So similarly, you know, if I look at oh sorry, this is too much. What was this? Okay. So similarly, now if I look at you know, this entry, again I get 0. Okay. Now what about the top left? So alpha plus alpha is 2 alpha, right? And what is this? Delta. Yeah, delta plus delta is 2 delta. So I get 2 alpha plus delta, which is what? So this is 1, isn't it? And similarly here I get 2 alpha plus delta. So this is also 1. So this is half 1001, right? And this is maximally mixed. So this is our quantum one-time pad. Okay, so we have seen key agreement, and we have seen, so let's use key agreement to agree on the key, and then we can use this one-time pad in order to send a quantum state with perfect security a single time, use up the key in doing this, right. So we can never again use this key.